Welcome to EDU World Space.
Before we start, let me just start with a clear whiteboard. So to calculate the total potential energy for the adenine and thymine bond, we must first calculate the individual potential energies of both these molecules first. So the total potential energy is equal to the potential energy of the adenine bond, which is potential energy of the nitrogen and hydrogen bonds, plus the potential energy of the thymine bond, which is the O. Hold on, let me go back and find out. So the O, hydrogen, and nitrogen bond. So this is what the final expression should look like. So we should find out the total potential energy by the sum of the individual potential energies for both these molecules. So to calculate the potential energies of these individual molecules, let's start with this first. So, or actually, let's start with the thymine bond. So this first. So the potential energy of the bonds between hydrogen, nitrogen, and oxygen is equal to, once again, it's equal to the individual bonds between these atoms. So it's the potential energy of the OH bond plus the potential energy of the hydrogen, and nitrogen bond. So now, like if you plug in the expressions for which are equivalent to the potential energies, we find out that it is equal to, so the expressions that we use to calculate the potential energy is Coulomb's law, which is equal to Coulomb's constant times charge 1 times charge 2 over the radius between the two, or the distance between the two atoms, between the two nuclei of the atoms actually, and it's called the radius between the two molecules. So it's the radius in this case of the distance between the nuclei of the oxygen and the nuclei of the hydrogen, which we call radius, plus the Coulomb's law for the second potential energy, the potential energy of the hydrogen and nitrogen bond. So once again, it's the two charges over the distance between the two nuclei, the radius. Now that we have the expressions, all we need to do is just plug in values. So if we go here and we can actually factor out a couple constants, since both these expressions have the same constants for in certain cases, so we can just pull them out and make a factored expression. So it's the Coulomb's constant. Let's just plug in the values as well. So let's start with Coulomb's constant, which is negative 1.6 times 10 to the negative 19. Once again, we see that the charges in both these expressions, there is one charge which is there in both these expressions, which is the charge of the hydrogen atom, which is equal to 9 times 10 to the power of 9. Now that the common terms are taken out, we can finish the expression. So the charge of the second one is 1.6 times 10 to the power of negative 19 over the radius of the OH, which is 0.28. So these are actually just constants, so you should have some place to refer to find these radiuses between the molecules, since they're just constants, and there's constants, so you should have some sort of reference when you're doing these types of problems. So it's 0.28 times 10 to the power of, let me check again, negative 9. So then if you do plus this, so now the second part, which is just, again, 1.6 times 10 to the power of 19, negative 19, over the radius between the two bonds, which is between the two atoms, which is 0.17. times 10 to the negative 9. Alright. So now if you plug this into a calculator, we find out that the potential energy of the OH of the thymine, or this is the thymine. Let me just remember. No, this is the adenine bond, which is equal to negative 4.45. Let's just put this in scientific notation so that's easier for us to understand. So negative 4.45 times 10. It's actually, sorry, I'm getting ahead of myself there. That's actually negative 5.32 times 10 to the negative 19 joules. So now that's the first molecule. So now moving on to the second one, we have the adenine bond, which is once again equal to the individual potential energies. So NH, and we also have potential energy of the nitrogen bond. Once again, we use a similar expression as this, so I don't think I need to write it again because the only thing that changes are the different constants, since the radiuses and charges are a little different for this expression. So it's getting right away into the substitution. We have so once again 9 times 10 to the 9 times negative 1.6 times 10 to the negative 19 . So it's 1.6 times 10 to the negative 19. So remember, the charge is based on the number of electrons the molecule has. So it's, sorry, this is a plus sign. I actually forgot to do the radiuses, so let's do that right now. So this is over the radius of the nitrogen, the radius between the nitrogen atom and the hydrogen atom, which is once again a standard number, which is 0.19 times 10 to the negative 9 plus, so this is 1.6 again times 10 to the negative 19 over 0.3. Let me write the 3 a little bit better there. 0.3 times 10 to the negative 9. So once again, this is the radius between the nitrogen and nitrogen. So now if you plug this into our calculator, we're going to find out that the potential energy for the adenine bond is equal to negative 4.45 times 10 to the negative 19 joules. So now that we have both parts to this first initial expression that we wrote here, we can just add them together to get the total potential energy. So now, so UT, once again, let me just write that again, U N N H N, that's the first molecule, plus the potential energy of the next one, which is OH N, is equal to negative 5.32, and since the ending is the same for both these expressions, we can actually just factor out these numbers and add them together to just make it more understandable for you guys. So it's we can put this in brackets and multiply the whole thing by the 10 to the negative 19, since both of them have the same base, the same exponent. So this is equal to negative 9.8 times So now over here we have found and solved the first part of this question. So now to find the potential energy of the electrons and protons in the hydrogen atom. So now, let's just draw a little line here. So we've answered the first part. Now to move on to the potential energy, to compare it with the potential energy of electrons and protons in the hydrogen atom, we have the potential energy between let's just call it the electron and proton for now. Hold on, let me write that a little bit better. So the potential energy between the electrons and protons is equal to, so using the same expression, so Coulomb's law, we can directly plug the values in. So Coulomb's constant, which is equal to, we can do that and do the calculations in blue. So plugging in the values for Coulomb's law, so Coulomb's constant first, 1.6 times 10 to the negative 19. This is actually negative. Then times 9 times 10 to the power of 9. And then 1.6 times 10 to the negative 19 to the power of negative 19. Alright, over the radius, which is 0.0529, which is just the constant between the electrons and the protons, times 10 to the negative 9. And so if you put this in a calculator, we find out that this potential energy is negative 4.36 times 10 to the negative 18 joules. So now we have successfully solved both parts of this problem, and these are two answers. Let me just highlight those in green. So here's our first answer for the potential energy of the thymine and adenine bond, and this is the potential energy for the electrons, for the potential energy of the electron-proton pair in the hydrogen atom.